This module is about probability chains. This has an enormous range of applications. So, for example, if you go to Google and you search for a book, a movie, or whatever, the system is going to take a certain amount of time. But if somebody else has searched for it, and if many, many people have searched for it, then that combination of words, of letters, then gets an enhanced probability, and so the search becomes faster. Similarly, if one looks at a word processing program or a dictionary, then again, these search algorithms are designed to give you the answer as fast as possible. They use what are called Markov chains. Markov was a Russian mathematician. He died about 100 years ago. The idea of the Markov chain is actually very simple, but it's something that we shall have to understand step by step. Now, of course, this is a huge area, and we'll just be able to scratch the surface of this. And so I hope that after this lecture, you will have enough background to go and read whatever particular application of Markov chains you might need in your work. To proceed, we will need the concept of a state, transitions between states, and chains of transitions. Well, let's begin with the state. The state of a system is said to be known when we know all the quantities that are needed to specify it. So if there are n possible states of a system, capital N, then the index I will go from 1, 2, 3 all the way up till n. Let's take examples. So a psychological state could be happy, sad, angry. 3 possible states. Or if you were to take the thermodynamic state of a gas, then you would state its temperature, pressure, volume, entropy, that is to say, all the variables that define the state of a gas. There are countless examples, and we shall encounter some shortly. Between states, we can have a transition. Now, a system can go from one state, let's call that I, to another state, let's call that J, and of course J could be the same as I. Now, if this transition is random, or what they call stochastic, then there will be some probability to transit from state I to state J. We will call this the transition probability Pij. So from I to J, we write I first, J second. Well, you could go from state I to state J to state K to state L. That will constitute a chain of transitions. We'll denote the number of steps or the transitions by the small letter n. This will be the length of the chain. Now, there's no limit to the length of this chain, so n can be 0, which means no step, you're in your original state, or you can take 1 step, 2 steps, any number of steps. These have to be countable, but the concept can be generalized beyond that as well. Now, that's for any chain, but a Markov chain is one in which the transition probabilities out of a given state of the system do not depend on how one got into that state. In other words, if you got into one particular state from some other state, it doesn't matter how you got into that state. In other words, there's no memory. If there is no memory, then that chain is called Markovian. Let's take some particular examples. So we've already encountered this man who has had a bit too much to drink, and he can take a step to the right with probability P, or he can take a step to the left with probability Q. P plus Q is equal to 1. He's got to move to the right or to the left. In this situation, we can define state 1 as the move towards the right, and state 2 as a move towards the left. This can therefore be written in the following way. Probability of right to right is P. Probability of right to left is Q. Probability of left to right is also P, and left to left is Q. We can represent this in terms of a diagram. So suppose that he is moving right, then the probability that he will keep moving right is P. So right to right is P, as denoted over here. Right to left is this probability, that's Q. While moving to the left, he can keep moving left like this. Left to right, so that is P. Let's now see how chains are made for this system. Here he has moved to the right, again right, then left, right, left, left, right, left, left, left. The probability for this particular path is obvious. It's P for every time he moves to the right, Q for every time he moves to the left. And so if you just multiply these together, you see that you get 4 P's, 6 Q's, and so this is the probability for that particular path. Again, this was a 2-state system. Capital N is 2, and there were 10 steps, or this was a chain with length 10. To establish the notations and get some concepts, let's look at a system which has got n equal to 3 possible states. State 1, state 2, state 3. Now here are the probabilities. If the system is in state 3, then the probability that it will remain in state 3 is P33. The probability of going from state 3 into state 2 is P32, and from 2 to 3 is P23. So we can write arrows for all of these probabilities. Another example, to go from 3 to 1 is this, P31, and to go from 1 to 3 is P13 with the arrow directed into 3. Let's take examples of Markovian systems. So, for example, this could be a Markovian model for child behavior. While the child is playing, she can start eating. That's got a 50% chance, let's say. Or while playing, she can start crying, and that's got a 40% chance. Of course, it's possible, and that's a 10% chance that she will keep playing. Now suppose, while playing, she starts eating. Well, in that case, she can keep eating with a 60% chance, or while eating, she can restart playing with a 30% chance, or there's a 10% chance that she will start crying, and while crying, she can keep crying with 50% probability, and if crying, then she can, with 40% chance, start playing again. Now these, of course, are faked probabilities, but presumably if you watch children playing long enough, then you can come up with such values for the probability. These are represented here in this table. So playing to playing is 10% or 0.1. Playing to eating is 50% or 0.5. Playing to crying is 40%. And similarly for the other elements of this table over here. Notice that this is a square matrix. Now with only slight changes, there are so many different systems that can be thus modeled. For example, here's a Markovian model for atmospheric behavior. I've hardly had to change anything. So, if there's a cloudy day, then that cloudy day can turn into a rainy day with, let's say, 50% probability. If it's raining, then it'll keep raining with 60% probability. Then from a rainy day, we can go to a sunny day. From a sunny day, we can go to a cloudy day, etc., etc. All that one needs to do is change the entries in this table. So cloudy, rainy, sunny, and again, we get a 3 by 3 square matrix. There's a nice way to visualize Markovian systems. So imagine that there's a frog which can sit on 4 lily pads. 1, 2, 3, 4. The frog can jump from one to the other with certain probabilities, and so we can collect all of the probabilities in the form of a 4 by 4 matrix. We'll call that matrix P. Its elements are 1 to 1, 1 to 2, 1 to 3, 1 to 4, etc., 4 to 3, 4 to 4. This is a collection of probabilities, and we will call this the probability transition matrix. So, as we've seen earlier, the entry P32, for example, is the probability of the frog jumping from lily pad number 3 to lily pad number 2. Now suppose that the frog is sitting at lily pad number 3, and that means that it is certainly there. It has probability 1. Then we're going to denote this with what we will call a row vector. So this U is a row vector whose entries are 0, 0, 1, 0. This 1 denotes that the frog is definitely at number 3 with probability 1. Now that is the starting vector, and so we will denote it with this superscript 0. Then the frog starts jumping, and after jumping n times, this U of 0 will become U of n. This row vector will then have entries U1n, U2n, U3n, U4n. And of course, if this was not 4, it was 40, then instead of just 4 over here, we'll have U5, U6, all the way up till U40. Well, now let's see how matrix multiplication works out for this particular row vector and this probability transition matrix P. So, suppose that we multiply U0 with P from the right, then we have 0, 0, 1, 0 times this matrix, and now you know what the rules of matrix multiplication will give you. You will multiply this with this, this with this, this with this, and then this with this. Then you will repeat with this with this, this with this, this with this, this with this, and so you will end up with this row vector, P31, P32, P33, P34. Now, isn't that interesting? You've started with 3, gone to 1, started with 3, gone to 2, started with 3, stayed in 3, started with 3 and gone into 4. So, after one jump, which could be to any of the 4 lily pads, one ends up with this row vector. We will denote this row vector with this index over here. In other words, this n is a single jump, 1. Well, now ask yourself, what would be the probability of going from 3 to 2 after 2 jumps? That is to say, small n is equal to 2. We'll call that P32. Now ask yourself, how do you get from 3 to 2? What are the different possibilities after 2 jumps? First, you could go from 3 to 1, 1 to 2. Or you could go from 3 to 2 and 2 back to 2. Or go from 3 to 3 and then jump from 3 to 2. Or you could have 3 to 4 and 4 to 2. In every case, you notice that you have 4 here, 4 here, 3 here, 3 here, 2 here, 2 here, 1 here, 1 here. And this is suggesting matrix multiplication, and indeed it is exactly that. Check it out. What we had earlier after one jump was this row vector. That which you encountered earlier over here. And now when you multiply that row vector with this matrix on the right, well then again by the rules of matrix multiplication, you're going to get something like this. So look at P32. How did we get P32? We multiplied P31 over here with P12, P32 with this with this, and this with this. That's how we got this entry over here, plus of course this entry and this entry and this entry, but I'm just looking at this entry, which is the probability of going from 3 to 2 after 2 jumps. And of course, this is what we call the row vector U2, this being small n equal to 2 jumps. In effect, what we've done is multiply with P 2 times. To get U after 1 jump, we multiplied with P only once, like over here. Now after 2 jumps, we multiplied with P twice. And of course, it doesn't require a genius to say that for any initial probability vector U, the probability vector after n jumps is going to be this. So if you start with U and multiply it with P times P times P n times, then you will get the probability row vector U after n steps. Where in this chain is the Markovian assumption coming? That's over here, that these transitions are memoryless. So suppose that the frog is sitting over here. He doesn't remember how he got here. Did he come here after jumping from here or from here or from here? Or was he sitting over here anyway? The probability of his next jump is not conditioned by where he was earlier. And so therefore, we say that this is memoryless. What is it that we can say about these probabilities? Well, the first thing is that all the probabilities out of any state, I, must add up to 1. And of course, each probability, so the probability of jumping from I to j has to be less than or equal to 1, and it has to be positive. These probabilities must add up in the following way. So if you're in the ith state, then the probability of jumping from I to 1 plus the probability of jumping from I to 2 plus all the way from I to n, these must add up to 1. If you want to write this in a more mathematical way, well, then just use this symbol. So this is saying that if this is our probability transition matrix, then the entries of this row, if added together, should be 1. Similarly for this row, and this row, and this row, they all add up to 1. This means that there are n constraints and n squared entries. This means that the number of independent parameters that are possible for the probability transition matrix is n squared minus n. Now, a couple of important definitions. A regular Markov chain is one in which the transition probability matrix has only positive entries. In other words, 0 is not allowed. And, by the way, I've used the word sum. That's because if I take this probability matrix and multiply it by itself, maybe once, maybe twice, maybe n times, then it could be that at some point it will develop a zero. However, if there is some probability transition matrix that has no zeros, then this will be a regular Markov chain. Here's an example of a regular Markov chain, and you can see that there are no zeros here. A second important definition is that of what is called an ergodic Markov chain. It's also called an irreducible Markov chain. This is a Markov chain in which any state is reachable from any other state. So, for example, going directly from 1 to 2 may not be possible, but it may be possible to go from 1 to 3 and then to go from 3 to 2. If that is the case, and if I can go from 1 to 3 to 2 and 2 to 3 to 4, and if I can go from any state to any other state, then this will be an ergodic Markov chain. Now, here's something that is fairly obvious. Every regular chain, that is to say one without a zero in its probability matrix, is going to be ergodic because you can go from one to the other or to the other. But it is not necessary for an ergodic chain to be regular. In other words, you can have a zero. Let me give you an example. So suppose that I have a starting vector which is 1, 0. Now this transition matrix has got a 0 over here and a 0 over here, and so it might seem that you're not allowed to go to any other state. But let's multiply this with p and you get 0, 1. If you multiply it again, then you come back to it. So in other words, this is an ergodic Markov chain. You can go from the first state to the second state and from the second state to the first state. In other words, every state of the system is reachable from every other state. Of course, that's pretty trivial because there are only 2 states in the system. Let's work out an example of a regular Markov chain. Suppose that union leaders meet together and they vote to strike, that would be state 1, or to not strike, and that would be state 2. Whatever they agree upon, their vote is whispered then from person to person. Now there's a 15% chance that a person will change yes to no when transmitting it onwards, and a 25% chance of changing no to yes. So the probability transition matrix is the following: yes to yes, 85%, yes to no, 15%, no to yes, 25%, and no to no, 75%. Let's note over here that if nobody lies, then P would be a unit matrix of this form, 1001. In this case, whatever the union leaders decided would be transmitted faithfully, truly, onto the others. But as we see, the information is altered as it goes from person to person. Well, let's take 2 people now. So if the news is passed on twice, then simply multiply this matrix P by itself and you will get this. Multiply it 3 times, so P cubed then is this. Multiply it 4 times, you get this, P to the 4. And you see now that this entry over here is getting smaller while this is getting bigger. And this row and this row are becoming more equal than they were earlier. Here's P to the 5, and now you see it's becoming still truer. Now I'm going to skip 6, 7, 8, 9. Here is now 10. P to the 10 is 0.627, 0.373, and now you see how close this row and this row are becoming. Well, if we keep going and keep going, after we multiply this matrix by itself many, many, many times, an infinite number of times, well, that converges to 0.625, which is 5 over 8, and 0.375, which is 3 over 8. Of course, this plus this is equal to 1, and now you see that this row and this row have become the same. So why is this important? Let's say that the union leaders had decided to strike, in which case this entry over here is 1 and this entry is 0. The first person who transmits this on will result in this vector becoming distorted. Now that 1 has become 0.85 and that 0 has become 0.15. Now let's say that this is transmitted onto many, many individuals. Well, if that number becomes infinity, then we multiply the initial vector u with p to the infinity and we get this. So, although it was decided to strike, yet the vector becomes 5/8 and 3/8. But now let's take a different case. Suppose that it had been decided that there would be a 70% chance that there would be a strike and 30% chance that there would not be a strike. Well, in that case, the first person who transmits on that information will have distorted it so that now we have, instead of 0.7, 0.67, and instead of 0.3, we have 0.33. But by the time it has gone through many, many people, in that case, the final will be again 5/8 and 3/8. And now what's really interesting is that if it was decided not to strike, nevertheless, since there's a 25% chance of changing no to yes, what we will have after one person has transmitted it on is 0.25 and 0.75. But this takes the cake. After many, many people have passed this information on with their own distortions, we end up exactly at 5/8 and 3/8. The moral of the story is that real news becomes fake news eventually, unless the means of transmission have total integrity. What you just saw was an example of 2x2 matrices converging to a fixed matrix after that matrix is multiplied by itself an infinite number of times. However, this can be made much more general. So, suppose that P is some n by n transition probability matrix. It has no zero element, so this corresponds to a regular Markov process. Then, as n becomes larger and larger, the matrix p to the power n will approach some constant matrix, which we shall call U. The matrix U, denoted by capital U, will have all its rows identical to each other, and we shall denote those rows as follows with this U. Of course, the components of U will all add up to 1. Let's see how to go about the proof. Now, I will assume that as n goes to infinity, this matrix p to the power n exists and is equal to U. I shall tell you where you can find the proof for this, and I will prove this for 2x2 matrices only, but let's assume this for now. So, if this limit exists, then obviously p to the power n plus 1 and p to the power n multiplied by p are exactly the same, and this p to the n plus 1 you can denote by u, and you can denote p to the n also by u. So, for large enough n, these two being identical, we will have u is equal to p times u. Now, since the rows of p add up to 1, that is to say, this holds, therefore, if you take the rows of p squared, well, the rows of p squared can be got by just multiplying p with itself. So you sum over k over here, and that will be equal to 1 because this condition forces this. Further, we can show very easily that all the rows of u are identical, and this actually follows directly from this relationship over here, which you can write as follows. So it's p into u, just the usual matrix multiplication, being equal to u itself. So take any fixed value of I, that will be the row I, the same I over here as is over here, and then these are simultaneous equations with identical coefficients from which it follows that every row of u is the same. Now, as I said, u is a collection of row vectors u, and so therefore u can be written as u times p. Now, this is exactly what one calls an eigenvector, except that we will call u a left eigenvector because p acts this way on u to give you u itself with eigenvalue 1. Of course, the normalization of u is not fixed from this equation. In other words, any number times u will also be an eigenvector. These three properties follow very simply from this assumption that p to the power n exists and converges to u. Let me prove convergence for the specific case of 2 by 2 matrices. In that case, the most general 2 by 2 matrix that is real and whose row elements add up to 1 has the form before you. So P will be 1 minus A in A. Obviously, this plus that has to equal to 1. Similarly, in this row, we can write 1 minus B and B. And here the only restriction is that A and B be positive numbers and that they be less than 1. Let's take the difference between row 1 and row 2 for each of the matrices that I'm going to write below. So, of course, P to the power 1, if I take the difference between this and this, that's what I get. Now notice over here that I have A minus B, either with a minus sign or a plus sign. And since A and B are both positive numbers, therefore A minus B is going to be smaller than A and smaller than B in terms of magnitude. So in other words, I'm getting something smaller than either A or B by taking their difference. Smaller in the sense of magnitude. Well, let's go to P squared. If I multiply P by itself and then look at the rows and take their difference, then I will get A minus B squared and the same thing with a negative sign. Now this, I have argued, is small, smaller than A or B, and this will be still smaller. Let's go to P cubed. In that case, I get A minus B cubed. The sign doesn't matter. P fourth, I get A minus B to the power fourth. So each time that I multiply the matrix by itself and take the difference between row 1 and row 2, I get something that is smaller and smaller. And now, actually, we can generalize this to any n and prove by induction that p to the n, if I take again the difference between row 1 and row 2, then I'll get something like this, a minus b to the n, and then the same thing here with a minus sign. So we have actually proved the theorem because a minus b to the power n goes to 0 as n goes to infinity because a minus b is less than 1. Hence, the rows of p to the n eventually become identical. Now this proof holds only for 2 by 2 matrices. However, for a general proof with n by n matrices, and it's a very clever proof, you should see Grinstead and Snell, chapter 11. Finally, let me come to absorbing Markov chains. By definition, a Markov chain is absorbing if it contains one or more states that can be entered into, but from which exit is impossible. So, if p I to I is equal to 1, that means I to any other state will be 0. Therefore, if you enter the state I, you can never leave it. Let me give you an example of an absorbing Markov chain. So, suppose that this is the probability transfer matrix. It's got this row over here. You can see that adds up to 1. This row adds up to 1. So does this. So does this. But here there is a 1. Let's look at this pictorially. So if you start from 1, you can go back to 1 with 20% probability, or you can go from 1 to 2 with 40% probability. You can go from 1 to 3 also with 40% probability. And then there are transitions into 1 which are possible from 2 or from 3. 1 cannot go into 4 directly, but it can go into 4 by way of 2 or by way of 3. Now let's see what happens when I take the square of p. So in other words, when I make 2 jumps starting from anywhere. In that case, p squared becomes this. One gets this, of course, by numerical multiplication on a computer. P cubed is this. Now there's no space over here for me to write P4, P5, etc., but I'll write P20, and here you can see that this entry or these entries are getting smaller and smaller, as are these, and if you go to P40, P50, P100, and then P infinity, this matrix converges finally to the following, with zeros everywhere except in this column over here. To see what this means more clearly, suppose that we start with the system in state 3. That is to say, the initial row vector is 0, 0, 1, 0. All probability 0 except this, which is 1. In that case, as we discussed earlier, the probability row vector after n steps will be u0 with p to the n multiplying it from this side. And now let's take n equal to 1. In that case, u1 will be simply this. u2 will be here. u3 is this. u4, u20, and now we have u infinity. So we started off in state 3 and we ended up in state 4, and now there is no way that the system can leave this. This over here is the endpoint. This is an absorbing Markov chain. After an infinite number of steps, one will land up most definitely in this state, in state 4.